Getting ready 6, we're going to compare linear, quadratic, and exponential functions. Okay. So this graph on the right, which is comparing time and distance of two cars. First question, which car has the cruise control on? Now, I know you don't drive yet, but cruise control is when you can set the car at a certain speed and it will maintain that speed. It will brake for you, it will feed gas for you to maintain whatever speed you set. So what we're looking here for is something that has a constant rate of change, a constant speed. Okay, so that one would be car A, and we know that because it's a line. It shows the constant rate of change, a constant speed. Number 2, which car is accelerating? Accelerating means to pick up speed, to gain speed. So that would be the one that is not straight, that is changing its speed. So that's car B. Okay, and that's because it's a curve. Speed is not constant. Identify the interval in figure 1 where car A is going faster than car B. Now, here, this one could be tricky because it's very tempting to think one of two things. To think that faster means wherever the graph of A is above the graph of B. That is not the case. If you look at the y value, the label on the y-axis here, it's distance. So that shows how far away the car is. But being further away doesn't mean it is still going faster. If we look at the beginning of the graphs, car A had a greater distance before we even began. So we do not, it's not relevant which graph is above or below the other one. Also, it's tempting to think that those two intervals, if we're reading question 3 and 4, the intervals where each car is going faster, that we have to switch over right here where they intersect. But again, that's about which graph is above or below the other one. That has nothing to do with the one going faster. So how do we tell? Since the labels here, the variables being compared are distance and time, when we put them together, distance over time, that is speed. So we're looking at how steep the graph is, each graph is, to determine which one's going faster. So I traced over the graph for car A so that I could move it down here and line it up so they both started at the same place, graph A and graph B. So if you look at my green line that I moved down to start the same place as graph B, we want to see for how long in this figure is the green line steeper than the curve. And again, it's not about where they intersect, but where the curve became steeper. And it's not an exact science here. We're just trying to use our judgment. I feel like the curve is less steep as I read left to right until about right in here somewhere. And then it seems to be steeper than the green line. So we might say that it's from the beginning, from 0 to, I don't know, about 1.3, 1.4, 1.5. So that interval would be until x gets to about 1.3, 1.4, whatever value you chose. The interval where car B is going faster is everything after the value you chose in number 3. So if I said that car B picked up speed and became a faster speed at 1.3, well then I would say that everything after 1.3. So what in the graph indicates that? And that is steepness. Okay. You don't have to have the exact same value that I do, the 1.3, but you should make sure that the value you chose for number 3 is where your interval starts in number 4. All right, then number 6, we're adding in a third car, this graph C, And we're looking to say if they maintained the speeds, the pattern that we see, and we were looking to go a distance of 12 units, then which car would get there first? So I already extended the y-axis here. Hopefully you don't even have to do that, but if you need to visualize it, 10 units would be exactly where I located the 10, and 12 is exactly where I put the 12. So if we tried to extend each of these graphs, now this is going to be freehand, rough, the line A is not going to get to 12 for quite some time. I'm way off the paper, off the grid by the time I could get to 12. So it's really between, it's down to either graph B or graph C, the two curves. Well, graph B looks like it may hit, I don't know, at about 1, 2, 3, 4, 5 to 6 units of time. The graph C, which starts off pretty flat, but then picks up speed tremendously, I would say that that one is probably going to get to 12 before the green one does. It's close, but I would think that car C reaches 12 units first. Okay, and to justify that, it's just something about the steepness that graph C, although it started out very flat, it got very steep very fast. So I think car C is exponential. Okay. I don't have any exact points there to verify that it definitely is an exponential curve, but it sure looks like it to me. And the green one, car B, it sort of looks quadratic to me. It's curved, but not as steep as the blue one. So the exponential is going to grow faster than a quadratic. All right, now we're going to start choosing some domain and range. Remember, sometimes we list points, sometimes we use interval notation. So in number 7, we have a piece of a line here. It does have endpoints at point A and point B. So the domain and range start and stop at certain places. They do not continue beyond what we see. So domain is the x's. So the leftiest point on this graph is -1, the rightiest is +1. So from -1 to +1, since there are solid dots at both of the endpoints, we include the -1 and 1. For range, the bottomest point is located at -1. The toppest point is 3. So -1 to 3. And again, since those are solid dots at each endpoint, we include the -1 and the 3. You can use either y or f of x when you write the range. Number 8. Now notice in number 8, these arrows indicate that the graph continues beyond what we see. It continues to rise and go to the left and to the right. So my domain would be all real numbers. The graph continues to the left and to the right. The range, now that one is not all real numbers because I do have a lowest point. There's a bottom to this graph down here at point A, that point 3, -1. That's the lowest, the minimum, but it continues up infinitely. So I would say that my range is all y values greater than or equal to -1. I do need or equal because there is a point at -1. Number 9, this oval or ellipse shape. We do have a bottom and a top and a leftiest and rightiest point. So neither the domain nor the range will be all real numbers. So the leftiest point here is at -4. The rightiest point is at 2. We're talking x values. We do get to -4 on the left, and we do reach 2 on the right, so include those. Do the same type of thing for range. The lowest value we reach is -2. the highest value is positive 2. We're talking y values. And since we do reach negative 2 and 2, we include those endpoints. All right, this is a parabola, sort of like we have graphed for quadratic functions, except this one is sideways. You won't really look at those in depth until geometry. So the domain, again, the leftiest, there is no leftiest value. The arrows indicate that it continues to the left forever. But we do have a far right point, and that happens at 2. So for the domain, we have all x's lower or equal to 2. For range, because the arrows indicate that it decreases and increases off our grid that we're showing, it goes forever, so the range would be all real numbers. Okay, number 11, we have array here. So we have one endpoint at -6, -2, but an arrow indicating that it continues to the right infinitely. So our domain is every x value starting from -6, continuing infinitely. So we say all x's greater than or equal to -6. Now, the range value, for a flat line like this, a horizontal line, every y value, if you were trying to list every point on this graph, the y values would all be the same. Every point has a y value of -2. So the range is just -2. We're going to kind of turn that around for number 12. In this one, all of the x values are the same. It's a vertical line. So again, if you started listing points on this graph, every point you wrote down would have an x value of 2. For range, our lowest point down here is on, let's see, it's one box up. Since it is 5 spaces, 5 scale markers to get to 2, 2 divided by 5 is 0.4. So that means our scale here is actually counting by 4/10. So that's our minimum. Our lowest value is 4/10. Our highest value, our maximum value is 6. Now, this is a little different because there's a solid dot on the 0.4, meaning we include that one. But an open dot up here at y is equal to 6. That means we don't actually reach 6. We get to 5.999999, but we don't hit 6. So do not include the right-hand value there, the 6. Okay, number 13. We have a line, and they did not specifically indicate with large black dots endpoints, but I'm assuming that they wanted us to end that line where we see it stop. So this one, our domain would go everything from -1 to 3. I'm assuming, again, since there are no open dots, that we do have values at -1 and at 3. For the y values, for the range, the top value is 7, the bottom value -5. So everything from -5 to 7, include both. Now that was a continuous graph. The second figure here, figure 2, has some of the same points we saw in that line, but they're not connected. So this is a discrete graph, a discrete function. So we have to just list our domain and range. So this time, our domain, the x values would be -1, 0, 1, 2, and 3, and nothing else, just those 5 values. The range values, same idea, we just list them. It's -5, -2, 1, 4, and 7. So the follow-up question, are the domains the same? And same thing could go for the range. So this domain for the figure 1 said everything from -1 to 3. This domain started at -1 and ended at 3, but it does not say to use that we did use all of the x values between those. We only used 0, 1, and 2. We didn't use any of the decimal or fraction rational numbers in there. So no, these domains are definitely not the same. In figure 1, we have a continuous function, and in figure 2, we have a discrete function. That means we are including everything in figure 1, everything from -1 to 3. And the discrete function, we're including only the listed values. Very different.